Hi everyone, Mrs. Basega here, and today we're looking at the Unit 2 Dynamics Test Review. If you haven't used this video and review packet combo before, what I'd like you to keep in mind is I'd like you to try all of these problems first, then check the answer key, and in this video, just skip forward to the questions you're having trouble with. You don't have to watch the whole thing, unless you want to. I also include this objectives list. It's a list of all the types of questions I'm going to be asking you. A good thing to know as you go is you could be like, oh, I can describe the relationship between velocity and acceleration. Give yourself a little check, and then only study the things you feel like you're uncomfortable with. So maybe you go through and you're like, oh, I can tell that acceleration is positive, negative, or zero from the shape of a position versus time graph. Right? Maybe you're like, all right, an upward facing curve is positive acceleration. I feel pretty good about that. Then go back, figure out what you don't know, and only study those things you feel least comfortable with. Problem one, we have a person that's either pulling up on a box or pulling down on a box. The reason this question is important is if you pull up, then the y component of your applied force is going to be helping to support the weight, the 50 Newton weight of the box. Because the y component is positive, well, it'll be helping support the weight. So in A, the normal force is smaller than 50 because the applied force is pulling upward. However, in B, the applied force is pushing down. The y component of applied force is actually working in the same direction as the weight. So the normal force has to be larger than 50 to compensate. In fact, if you think about it, the normal force would be the weight plus whatever this y component is. So in B, the normal force would be bigger. As a result, if the normal force is bigger, that means there's more friction in B. Now, why that is because friction only depends on two things: the material, symbol is mu, and the normal force, pushing those two surfaces together. There is a direct relationship between normal force and friction force. So B has more normal force, B has more friction force. In number two, I'm asking you to plot two different graphs, Chris and Pat. So what I'm going to do is let's start with Chris. Chris accelerates at 2 meters per second squared and has a top speed of 8. So for every second of time that goes by, starting from 0, Chris starts at rest and adds 2 meters per second every second of time that passes up until they reach their top speed of 8. An acceleration of positive 2 means it adds a velocity of 2 every time. With a top speed of 8, they then run at 8 for the remaining of all the remaining points. So if I draw this out, Chris has the greater acceleration. So I'd be plotting the point 0, 0, 1, 2, 2, 4, 3, 6, 4, 8. Then Chris goes constant velocity the rest of the time. Pat accelerates at 1 meter per second squared, up to its top speed of 12. So doing the same sort of logic here, their initial velocity is 0, but every second of time that passes, the velocity increases by 1, all the way up to 12, which occurs at, obviously, 12 seconds. Afterwards, Pat stays at a velocity of 12 for the rest of the time. So if I go up to the point 12, 12, we can kind of skip plotting every point here. Now, the fun fact is we have to figure out who is ahead. All the questions that remain are asking about like who is ahead at some point, who's ahead at the end of the race. all of these have to do with distance. The way we calculate anything measured in meters from a velocity versus time graph is calculating the area under the curve. To figure out who's ahead, I am thinking who has the greater displacement at 8 seconds. And in order to calculate displacement from a velocity versus time graph, I'm going to do area under the curve. So in this case, the area under the curve for Chris is going to be taking the area from the function, so that's this trapezoid right here, shading down to the x-axis here. But for Pat, the area under the curve would be tracing the function for the first 8 seconds and shading down to the x-axis. Hey, notice this for me. If you look at the overlap, I can see without doing any math that Pat's area under the curve is less than Chris's area under the curve, at least for the first 8 seconds. I actually don't need to calculate this out to see that the areas are different. Chris traveled farther because the area under the curve was bigger for Chris. So who is ahead? Chris has the greater displacement. Well, the end of the race is a different story. By the end of the race, check out these areas. Chris would be taking the rest of this distance as well. Pat would be taking even more area under the curve right here. Those are not far enough different that I can just eyeball which one is bigger in my head. So I actually will calculate this. Pat's area under the curve is the area of a triangle plus the area of a rectangle. Pat's area under the curve goes for 12 seconds with a height of 12, and then 8 more seconds with a height of 12. So if I add this up for displacement, it's a triangle with a base of 12 and a height of 12, plus a rectangle with a base of 8 and a height of 12. Mathing this out, 72 plus 96 equals 168 meters for Pat. Going back to Chris, well, that's also a triangle plus a rectangle, a really steep triangle for the first 4 seconds with a height of 8, and then the next 16 seconds at a height of 8. The area under the curve for Chris then would be 1/2 a base of 4 with a height of 8 plus a base of 8 times a height of 16. Mathing this out gets 16 plus 128 equals 144. Comparing these two, Pat has a bigger displacement by the end of the race because they've traveled 168 meters to Chris's 144. The distance between the two runners by the end of the race then would be 168 minus 144. So by the end of the race, Pat is 24 meters in front of Chris. Next, we have a football. And the football is going to travel vertically, so it travels fast to start, and then slows down as it reaches the apex, speeds up as it travels back towards the ground, and it's going to do this until it reaches a velocity of negative 29.4 meters per second. Well, this is because the final velocity has to be equal in magnitude to the initial velocity. While it's in the air, this is considered a free fall problem. That means there's no other forces except for gravity. I would only put Fg. Think of it like this. The applied force is a contact force. That will not apply any force while the football is in the air, because it's not like the person's foot is still in contact with the ball. So only one force in your free body diagram, please. Next, for every second of time that passes, the velocity of this ball decreases by 9.8. That's the idea with something that's accelerating due to gravity. Every second of time that goes by, 9.8 is subtracted. That means actually as the ball falls down, it's getting faster and faster and faster in the negative direction. Just a quick review for speeding up versus slowing down. Speeding up occurs from 4 to 6 seconds because the velocity is negative and the acceleration is negative. Notice that the speed, the absolute value of this, is getting faster and faster and faster, just in the negative direction. So speeding up occurs where velocity and acceleration point in the same direction. If I were to graph this, I get a slope with a negative value. The velocity starts at 29.4, and for every second of time, the velocity decreases by 9.8, so that at 3 seconds, the ball has reached the apex. By 6 seconds, it's returned to the ground. Connecting our dots up, I'm basically plotting the values from above. The apex is at 3 seconds. The apex has a velocity value of 0, but that doesn't mean the acceleration is 0. Acceleration is the slope of this line. And since this is a straight line, you could pick any 2 points along this line, calculate the slope, right, and use that to get the acceleration. But that's kind of overcomplicating this, right? Because we used the slope. We actually already used this number. If you pick any 2 points along this line, the acceleration is going to be negative 9.8 meters per second squared because that's what we calculated up here, right? So the acceleration at the ball is negative 9.8 at the apex because it's actually negative 9.8 the whole time. The slope stays the same because the acceleration is caused by this constant force due to gravity. For G, how fast is the football going just before it hits the ground on the way back down? That was this negative 29.4 meters per second. This is because of symmetry. If it was positive 29.4 on the way up, it'll be negative 29.4 on the way down. How long does it take for the football to reach its apex? It took 3 seconds. Now, if you want to do this out with kinematics, and I'd like to remind you how to do this, we know that the ball starts from the ground with an initial velocity of positive 29.4. The final velocity is 0 at the apex, and the acceleration was negative 9.8. I'm going to try and use this to calculate time. So I'm going to use our acceleration equation. The acceleration of negative 9.8 is equal to 0 minus 29.4 all over t. Multiplying by t to the left gives negative 9.8t equals negative 29.4. Hey, those negative signs cancel, which is good because I shouldn't end up with a negative time. The time to the apex is 29.4 over 9.8 equals to 3 seconds, which makes sense because that's how long it took to get to a 0 velocity on our T chart. The total time for the football to be in the air then was 6 seconds. 3 seconds to rise to the apex, 3 seconds to fall back to the ground, for 6 seconds total by symmetry. Finally, calculate the maximum height. I can either do this one of 2 ways. We can do this with kinematics or graphing. And here's why I like the graphing method. It's just fast, okay? This is the area under the curve that represents the distance traveled from the ground to the apex. So notice I'm shading my function for the first 3 seconds of time, shade down to the x-axis. So if I want to do this graphically, I'm going to use area under the curve is equal to anything measured in meters, so displacement, distance, height. In this case, it's height. I'm taking a 1/2 of a base of 3 and a height of 29.4 meters per second. This gets a displacement of 44.1 meters. Now, if you'd like to do this mathematically, we can do that too. Totally up to you. Remember, mathematically, we're going to use kinematics. So we start with a height of 0, and we're trying to find how high this goes up in the air. The initial velocity was positive 29.4, but the velocity at the apex is 0. The acceleration is negative 9.8, and we do know from earlier that it takes 3 seconds to reach the apex. Because I have so many values known, I can actually pick either equation 1 or 2 to solve this with kinematics. I'm going to choose equation 2 because this is the one that's already arranged to solve for xf. So this says the height is equal to 0 plus 29.4 times 3 plus 1/2 negative 9.8, 3 squared. So do notice you end up subtracting here. Think like the 29.4 times 3 is the height it would rise to if it was not being forced to slow down because of gravity. It would have gone 88.2 meters up in the air. But because gravity is accelerating it, I have to subtract 44.1 meters due to this negative acceleration term. Subtracting those out, I've got a 44.1 meter height, and both methods agree. Number 4 is a friction problem. I've got a student pushing with an applied force forward, friction that acts against the direction of motion, normal force up, weight down. In this case, it does not indicate whether this is accelerating or not, so I'm not putting any marks on applied or friction force. B is asking a proportions question. It asks what happens if friction, or what happens to friction if the normal force is doubled? Well, check out our friction equation. There's a direct relationship between normal and friction. If I make normal twice as big, it makes friction twice as big. I often will write it like this. Doubling the normal force will double the friction force because of a direct relationship. This equation says the material affects friction and the normal affects friction, but not the other way around. Normal and coefficient do not affect each other. If I increase the normal force, it changes the friction force, but it does not change the coefficient. The mu for coefficient of friction, I want you to think the mu stands for material. If I put more kids on top of this sofa, or I make it a heavier sofa, it's still wood moving across the floor. This surface does not change, so the coefficient does not change. Now, when I say surface, I mean surface material. It's wood moving across the floor. But I don't want you to confuse surface material with surface area. What an equation like the friction equation means is that the friction force is solely determined by the coefficient of friction in the normal force. That means changing the surface area has no effect. Any symbol that's not in this equation means that there's actually no effect on this force. So if surface area is tripled, then there is no change, no effect to the friction force. This is saying that mu, the coefficient of friction, becomes smaller. As the coefficient becomes smaller, the friction force becomes smaller, because this is also a direct relationship. Replacing a surface with a very low friction plastic, well, that's like the physics behind those chair cushions that go under the bottom of your chair so they don't make squeaky noises. Now let's do some math about it. The student pulls on the 35 kilogram sofa until it starts to move. It moves at constant velocity across the room. It gives us two coefficients of friction and asks to find applied forces. Well, at the beginning, this applied force to start the sofa sliding, that's going to be using our static friction coefficient. Because it has not yet started sliding, it is still static. So when I solve this, I'm going to put in a 0.7 for mu. Similarly, in G, we want the kinetic friction force because it already is sliding. And what I'm picturing for my head is both of these cases are referring to times when the friction force cancels applied force. When the static friction equals applied force, well, that's static equilibrium, so the forces are balanced and it doesn't accelerate. When it's moving at constant velocity, the applied force doesn't make it speed up, the friction force doesn't make it slow down, and so that's dynamic equilibrium. So I would be using mu as 0.5 here. But there is a trick. I did not give you a normal force, but I did give you a mass. What I'm trying to get you to do is use the y direction of this. In the y direction, the normal force is equal to Fg. So I gave you the mass in kilograms. You need to turn it to weight. And because the weight is going to be equal to the normal force, you can use it in this equation. So the weight is 35 kilograms times 9.8. Remember that kilograms is the base unit for mass, so you don't have to convert this to grams. I can just do 35 times 9.8. So the weight of this object is 343 newtons. But so is the normal force because it's in equilibrium in the y direction. The static friction force in this case is 240 newtons. The kinetic friction is 171. One of the things the review packet doesn't practice, but you should probably keep in mind, is that this could be graphed then as the applied force increases to 240 newtons. Then, as soon as our object starts moving, the applied force can be smaller, can be 171 newtons, because the kinetic friction is less than the static friction. This would be a graph of applied force versus friction force. All right, we've got Bob the Builder here. Bob the Builder is pushing at an angle of 25 degrees below the horizontal. So I'm going to do my gravitational force down. Fa is down and to the right. And the normal force has to be bigger than gravity because it's going to take both the gravity's y component and this little y component from Fa. It has to be larger to counter two forces. Later in the problem, it implies that there is friction. So I'm going to put a little friction force right here too. Now notice all my forces are perpendicular to each other, lying along the xy plane except for Fa. When I'm asking you to draw the modified free body diagram, I'm asking you to take Fa and replace it with its components. So I'm going to keep everything the same except Fa is going to get replaced with x and y components. Fg is still this big. Ff is still this sized. F normal is still bigger and lying along that y-axis. But now I'm going to replace Fa with its x component to the right, which I'm going to call Fax, and its y component down. I know it's down because the angle was down and to the right. Calculating the weight is still Fg equals mg. It's 50 kilograms, with kilograms being the base unit for mass. G is 9.8 newtons per kilogram, the gravitational field of the Earth. So the weight of this wheelbarrow is 490 newtons. The components of the applied force, these go along with Fax and Fay. And I want you to notice that now I have to use cosine with x and sine with y. This was a force of 220 newtons at 25 degrees. 220 cosine 25. That gives 199.4 newtons, right? Fay goes with sine now, so that's 220 sine 25. Substituting that into my calculator gives 93 newtons down. But hey, now that I know some numbers, let's go back and look at the modified free body diagram. The gravitational force was 490 newtons down. The applied force was 93 newtons down. In the x direction, the applied force was pushing at just about 200, so 199.4 to the right. And now I have all of the numbers I need to find normal and friction force. See how in the y direction, the normal force has to be equal to both Fg plus Fay? Yeah, because it's an equilibrium. Like our wheelbarrow isn't sinking into the ground or rising up into the air. So in the y direction, equilibrium means that the normal force is equal to the gravitational force plus Fay, or in this case, 490 plus 93. The normal force then is bigger than gravity because it's also supporting Fay, and this gets something like 583 newtons up for normal force. Now, don't get tricked here thinking that Fax is equal to friction. The trick is the acceleration is 1. Because the acceleration is 1, Newton's second law says there must be an unbalanced force. The force was unbalanced because the applied force to the right is canceling the friction force to the left. The applied force to the right was 199.4. The friction force to the left is unknown, and the mass in kilograms was 50. I can solve this for friction force. Multiplying 50 to the left gives me something like 50 is equal to 199 minus FF. This leaves the friction force as 149.4 because I dropped the 0.4 right here. Friction should be smaller than normal force. The reason I suspect friction to be smaller than normal force is the coefficient of friction is always some number less than 1 for most normal objects. So if friction was larger than normal, my coefficient would be too big. Substituting into the friction equation, I'm going to divide by 583 to the left. So my coefficient of friction is 0.26, a number less than 1, just as we expect. Now, if our guy was pulling up at an angle, the weight would stay the same. That's because the weight is equal to mg. So the field doesn't change, the mass doesn't change, weight stays the same. But the normal force would decrease. If I were to draw the y components, gravity would still be down, but the y component of Fa would be upward, necessitating a smaller normal force. A smaller normal force means a smaller friction force, but the coefficient of friction would stay the same because the materials stay the same. We spent 2 days in class doing a lab on Newton's second law. It's one of the only specific experiments called out in the National Science Standards for you to do in this class. So the experiment's pretty important here, just saying. This person's doing a bunch of different trials, keeping mass constant. So I would say the control variable is mass. They were changing the force, so that's going to be our independent variable, and that force caused a change in acceleration. That must be the dependent variable. When the student says that they're trying to determine the relationship between mass and acceleration, that's not true, because if you look at your data, I would be plotting force versus acceleration, not mass. If they want to see if mass changes acceleration, they would have to change the mass, but they didn't. Same for C. The data showed there's no relationship between the applied force and acceleration. I don't agree with that either. I don't agree with that because this is a direct relationship. A good way to check to see if something is direct or not is to check the proportions. Is it true from the data that if you double the force, it doubles the acceleration? Yeah. And I might write this as saying, when the force doubled from 10 newtons to 20 newtons, the acceleration also doubled from 1.42 meters per second squared to 2.9 meters per second squared. This is even true for triples and quadruples. Tripling the force from 10 newtons to 30 newtons triples the acceleration from 1.42 meters per second squared to 4.28 meters per second squared. So their conclusion is incorrect. This is a direct relationship. A direct graph starts at 0, 0 and increases with a constant slope. This makes sense because I should have zero acceleration for zero force. So graph A is the graph between force and acceleration. Well, mass and acceleration is different. Even without the experimental relationship in front of you, you should know that more massive objects have more inertia, and that prevents them from accelerating. Graph D shows the relationship between mass and acceleration. Last one. Let's say we're looking at the Olympics and we've got our guy going down on the sled. The free body diagram should not show components. It should only show the value of the forces. However, the modified free body diagram can show components. The gravitational force is going to be the one in this case that's broken up at an angle. So I'm drawing normal force as just the same as before, but I'm going to replace FGX and FGY with their down the hill components, that's FGX, and into the hill components, that's FGY. FGY is always going to cancel the normal force, so that's good. I know we've done it 2 times already, but let's do weight again. The weight of an object is its mass times the gravitational field. So 80 kilograms of mass and a 9.8 Newton per kilogram gravitational field gives 788 newtons of gravitational force, or weight. Remember, those two are synonyms of each other. Now that it's an inclined plane, FGX is now going to go with sine. So take the weight of our object times sine of 30 degrees. That's 788 sine 30. Oh, quick typo here. 784 newtons. That makes this 392 newtons. Quick change. Sorry about that. In the y direction, FGY is going to be FG cos theta. So take your 784 cosine 30. FGY would be 678.9 newtons. Now that I have my components, let's go up to our free body diagram. We know FGY is 678.89, so that must also be equal to the normal force. FGX is the only force in this x direction, so that must be the net force causing the acceleration of our sled. So Fn equals FGY is 678.9 newtons, and the acceleration is F net over the mass. There's only one force causing the acceleration, and that acts on 80 kilograms of mass. This acceleration is 4.9 meters per second squared. That makes sense to me because I'm expecting an acceleration between 0 and 9.8. Finally, what happens when the angle increases? The weight would stay the same because Fg still equals mg, guys. Mass doesn't change, field doesn't change. But the normal force would change. The normal force would decrease. Remember that the normal force was equal to the weight of our object, which was unchanged, but times cosine of the angle. And as angle goes up, Cosine goes down until it reaches zero at 90 degrees. So my normal force would decrease if the angle went up. All right, folks, that looks like it's everything. Best of luck.